Morning, we're finishing the dwarf session that we started yesterday afternoon, and our first speaker will be Alyson, who's going to talk more about the Marvel-ous Dwarfs suite of simulations. Go ahead.
Thanks. I learned yesterday that I need to stand over here. So Charlotte introduced these runs a little bit yesterday, the Marvel-ous Dwarf volumes. And she talked about gas in these dwarfs, so I'm going to be highlighting a couple more things that we're doing with these dwarfs right now. Charlotte showed this movie yesterday, which is just for one of these volumes showing the dark matter density and the gas density, and we're zooming in here on the most massive thing in this volume, which is an SMC-sized galaxy. So it's not, it's maybe not as spectacular as a giant Milky Way or something. But I wanted to show it again for this, right? So people asked yesterday about the environment of these dwarfs, and you can see right here at the start that this really is like a cosmic sheet that these are coming from. So these aren't void dwarfs. So yes, here they are, Captain Marvel, Electro, Rogue, and Storm. Charlotte mentioned yesterday, right? They have a force resolution of about 60 parsecs, and we let the smoothing length go down about an order of magnitude smaller to 6 parsecs. Stellar masses, these stars are now forming with 400 solar mass star particles. They're all run to redshift 0, and they come in assorted flavors. So we've done all of them as dark matter only runs, and then most of the results I'm presenting today have a star formation prescription based on the presence of molecular hydrogen, and they also have black holes, massive black hole seeds in them. And I'm going to show some results where we ran Captain Marvel here with a different star formation prescription and what happens when you do that. An SIDM version exists in dark matter only for one of these runs. And I'm personally interested in running more of these in SIDM as well. But I need somebody to actually analyze them for me because I'm running out of manpower, I guess, woman power. Okay, so I want to highlight. So if you're forming star particles at 400 solar masses, it came up yesterday, of course, you're not fully populating your IMF when you do that. So I want to highlight that one of my grad students, Alad Applebaum, is giving a talk on Friday in the final session. But he has introduced a new form of the stochastic IMF. A lot of people are considering this problem, right, where you have low star particle masses and introduced a prescription where you have quantized supernova feedback, but Alad has actually done something totally different where he's actually tracking individual massive stars inside of star particles. So if you're interested in that, please stick around for Alad's talk. Also the black holes, right? So another of my grad students, Ray Sharma, will be giving a talk Thursday afternoon on black holes in dwarf galaxies. Not from these runs, actually, but from a big volume that we have called the Romulus 25. It's a uniform 25 megaparsec volume that Michael Tremmel ran. And he's actually finding some interesting things on demographics of dwarf galaxies with and without black holes. So here is, this plot is just designed to give you an example of the demographics that we get out of these dwarf volumes. So they are color-coded. These are all the galaxies with extended star formation histories, and they're color-coded by their V-band magnitude at redshift 0. You can see the most massive thing is roughly LMC-sized, but we actually form dwarf galaxies down to about 10 to the 8 in halo mass. And they are reaching the ultrafaint range, right? They're down to about 1,000 solar masses. So some questions came up yesterday about the fact that these are somewhat isolated, right? They are about 4 to 10 megaparsecs away from the Milky Way. There's still plenty of galaxies in the local volume that are also 4 to 10 megaparsecs away. But if you want to compare to things like dwarf spheroidals, you need a sample of Milky Ways. So we're also running Milky Ways at similar resolutions. So because we have the Marvel dwarf volumes, we thought we would also go to the other comic book, all right, publisher, the DC Comics. And so we decided that these 4 would be the DC Justice League runs. But we wanted to stick with the female simulation names. So we are going with Sonia, Sandra, Ruth, and Elena as our DC Justice League. So All of these have been run at sort of standard resolution for us at 170 parsecs. They're all done already at redshift 0, and so I'll be showing some results from that today. But they're also being run at comparable resolutions to the dwarf volumes at 85 parsec resolution. And yeah, all three of those at least are below redshift 1 already. So here they all are, again, with the about 170 parsec resolution Milky Ways and the dwarf volumes. Dwarf volumes are the bigger circles here, and the Milky Ways are the smaller circles. So this is what the full sample looks like. It's a couple hundred dwarf galaxies, right? Again, spanning LMC size down into the ultra-faint range. Okay. Charlotte showed some observational trends, scaling relations yesterday. I'm going to show just a couple different ones. This is the size versus luminosity, where we've got central galaxies separated out from satellite galaxies. And the circles here are all local group or local volume data, mostly from McConaughey. The black circles, the filled in ones, are DES dwarfs. And so you can see we actually resolved dwarf galaxies here down to 100 parsecs in size, right, with like more than 40 star particles. So, yeah, pretty much what I want to say. Joel asked about the H1 masses yesterday. So here's the H1 mass as a function of B-band luminosity for these simulated dwarfs in red compared to data from the FIGS and the FIGS2 surveys and SHIELD. And so they're doing a really nice job of matching observed dwarfs as well. Charlotte showed some of these already yesterday, the star formation histories and cumulative star formation histories. A little more quantitatively, here is the specific star formation rate of these galaxies at redshift 0 as a function of stellar mass. And we can compare it to data from Christy McQuinn's sample, and they're doing a nice job of matching the data there. Here is the recent star formation rate compared to the past average star formation rate of these dwarfs. And again, here is Christie's data in gray points. And so they're looking realistic in terms of their star formation histories as well. Okay, so now let me jump to some of the things we're doing with these dwarf galaxies. One of the main things we're interested in is what is happening down here, right, in the stellar mass to halo mass relationship at low masses. Farah Munshi and collaborators had a paper out last year looking at this, but only in one of the volumes in Captain Marvel. And now you can see this is what it looks like with the full sample. Basically, the results don't change. We still find a scatter up at the high mass end of about 0.1 or 0.2 dex, which is consistent with the observations. But as you get below halo masses of about 10 to the 10, the scatter really blows up. All right, so this is a log normal scatter of about a dex down here. And really, that's a lower limit, right, because we're hitting our resolution limit in terms of how many star particles we can form down here. So it could actually even be bigger scatter than that. Now, why do we care? Why do we care about the scatter at the low mass end? Well, I'm going to highlight Shay's work, actually, because Shay showed really nicely why we need to care about the scatter in the stellar mass to halo mass relationship. Here's an example of two different stellar mass to halo mass relationships. The magenta line here has a more shallow slope, but no scatter in it. And the blue line here has a steep slope, but with 2 dex of scatter. Okay. So it turns out that that has a big impact on the resulting stellar mass function. Both of these, even though they have such different slopes, are fully consistent with the observed stellar mass function. And that's because when you take into account the scatter, there are more small halos than large mass halos. And so you're more likely to scatter in one direction. You scatter small halos up instead of large halos down. Fewer large halos go down. And so you need a steeper slope in order to reproduce the stellar mass function if you have scatter. So if I take the scatter that we found in these simulations, all that scatter showed up in the ultra-faint range. Right? So here is an example of the stellar mass function that we predict with no scatter. Here is the scatter that we predict, the stellar mass function that we predict with scatter. And in gray is highlighted the mass range of the dwarfs that have been found by DES. So it's really in the ultra-faint range. So this is a prediction. We think as we find, as LSST comes online and we find more of these dwarf galaxies, just in terms of pure number counts, we think we're going to see the effect of scatter in the stellar mass to halo mass relationship. So let me turn to another result that we're doing with these dwarf volumes. I'm now highlighting in stars all of the dwarfs here that ended up with massive black holes in them. And so we have a prescription that basically looks like a direct collapse model for black hole formation, where if you are a gas particle that is cold and dense and also basically metal-free in the early universe, then there is some chance that you will form a massive black hole seed. It scales with resolution of the simulations, right? So in here, it's about 10 to the 5, I think. So these are the ones that ended up with massive black holes. Jillian Bellavary has already done an analysis on these and has a paper out on arXiv. Essentially, these dwarf black holes don't grow much, right? They don't have a whole lot of accretion in their histories, which I think is the picture that most of us have in our head for dwarf galaxy massive black holes. They're probably not too important in the evolution of dwarfs, we tend to think. Though C. Ray's talk, he may actually be finding something different than that. But it is true that in these runs, these black holes don't grow very much. And so when they merge together, when a couple of black holes actually merge together, it's seed mass black holes that are merging together. And so some of this is happening, basically it's happening at all redshifts, but some of them are also happening at early times in the dark ages. And we think that these are actually in the mass range where they would be detectable by LISA. So Jillian is making predictions for mass merger rates and mass ratios that should be detectable by LISA. And so the final thing I want to talk about, final results that we are currently working on from these runs, is what happens when you use two different star formation prescriptions. So here is the Captain Marvel version. And actually, this plot over on the right is the prescription that I've been presenting so far. It's where star formation can form if you have molecular gas present. Okay. But this is the same run over here. And now we have introduced another common prescription, right? It's common for simulators to say, well, I'm just going to form stars when I get above some density threshold and below some temperature. So here, stars can form if they are greater than 100 AMU per cc in density, and they are cold. And if you look at the massive end, there are a bunch of dwarfs that basically came out very similar. They're matched across the two runs. But as you go to lower halo masses, there's a pretty big difference, right? There's actually way more galaxies forming in this prescription than there are over here. So here's another way of looking at that. This is now where I've traced back the maximum halo mass that these things ever sat in and the number of stars they had at that time. The black circles are the molecular run. Metal cooling is the empty circles. And the metal cooling run actually forms a whole bunch of things down here with 1, 2, 3, 4 star particles that we don't even consider resolved. And they're not even included in the plot I just showed you. So we'll just throw those out and say those star formation histories aren't resolved. But up here, these things all have 10 or more star particles. And so we consider them decently resolved, at least. And if you look at the high mass galaxies, right, the lines connect matched galaxies across the two runs. And so up here, both of these simulations basically make similar dwarfs. But as you go to these lower masses, now you can see that the molecular run actually produces a lot less stars at these lower halo masses. And there are a bunch of halos that don't even form stars in the molecular run, but do in the metal cooling run. So let me just jump to why this is happening. Right? So here's the phase diagram of gas particles that go on and form stars in these simulations in the first billion years. So this is just stars that formed in the first billion years. But in gray are the gas particles that form stars in the metal cooling run. And in black and the contours are stars in the H2 run. And you can see there's certainly some overlap, but as expected, probably, the metal cooling run, right, is allowed to form stars when it gets above 100 AMU per cc. So you're seeing most of the stars are forming there. In the H2 run, on the other hand, most of the stars are forming at about 1,000 AMU per cc or higher. Okay, thanks. So this is based entirely, this is the physics of the molecular gas formation, right? So these are dwarf galaxies in the reionization epoch. They are incredibly metal poor. And so for H2 to form, you have to get above these high densities. So forget for a moment that I'm talking about these two specific star formation prescriptions. Really, what I want to point out is that all simulators pretty much in this room are adopting something like this, right? No, both, right? So some people are doing, well, I'm going to form stars when we get above 100 AMU per cc. Fire 1 did that. Fire 2 is above 1,000, right? So we've got a mix, I'd say, of people doing different things in this room. Nihao is down around 10 to 100, things like that. So this really applies to all of us, right? We're all doing things a little bit differently. And people have looked at this before. So, we acknowledge we all have different star formation prescriptions. What is the effect? Well, people have looked at it in this mass range, right? So Phil Hopkins and collaborators looked at it, and they found basically the star formation prescription made no difference. Right? And James Wadsley and collaborators have looked at it, and they found the star formation density basically made no difference. And here's another example from one of Charlotte's 2014 papers, where she ran a dwarf galaxy of about 10 to the 8 in stellar mass. And here's the H2 version in red, and the metal cooling version in black, and basically you end up with the same galaxy. Here's kinematically, the rotation curve is similar. Here's the outflow rate. It's actually similar in both those runs to within a factor of 2. So there's very little difference in this mass range. Okay, and that's because galaxies above some mass are generally able to self-regulate. If you tweak one prescription, the feedback just compensates, and you end up producing galaxies with similar stellar masses. So what we're seeing here is that we're seeing this for the first time because nobody's actually looked at ultra-faint dwarf galaxies in cosmological simulations until now. Right? So below a few times 10 to the 9 in halo mass, your galaxies can no longer self-regulate. And so this isn't surprising. We're now reaching into a range where these are halos that are going to be affected by reionization or supernova feedback. And so that's exactly what we're seeing here. Because the metal cooling run can run with lower densities, can form stars at lower densities, it starts forming stars before reionization really affects the halo. In the H2 run, on the other hand, because it has to reach these higher densities, reionization actually stops it from forming stars or as many stars before reionization kicks in. So we no longer are seeing convergence in this regime. So this has implications, obviously. Basically what I'm saying is, you shouldn't, whenever you read a simulation paper, and if you're worrying about ultra-faint dwarfs, you need to be considering this, right? What is their star formation prescription? Because it clearly matters in the ultra-faint range. So let me come back to this picture here and point out these stars, right? So I didn't say earlier what these stars are, but they're satellites. Okay, so this is exactly what Coral was talking about yesterday, the ultra-faint dwarf satellites around dwarf galaxies. In the molecular run, we have 2. And in the metal cooling run, we have 10. So we have a factor of 5 difference in the number of ultra-faint dwarfs that are forming. So we can play the same game that Coral did in her 2015 paper, where you go to Elvis, you pick out roughly SMC size galaxies, or halos, I should say, in the dark matter only catalog, and then ask if I populated them based on the occupation fraction I see in these runs, how many dwarf galaxy satellites do I expect around something like an SMC-sized halo? Coral's original paper was run with Fire 1, and so it had a prescription, again, where stars were forming above 100 AMU per cc, so similar to the metal cooling run. So maybe that's why these two distributions are fairly similar. But when we go to the H2 run, right, we kill a bunch of those halos. We drop down to about 15% expected around something like the around 15% of SMC-sized galaxies should have an ultra-faint dwarf companion, and we don't even see any that have more than one. Okay. So let me comment on the LMC, because the LMC came up yesterday. This is not prediction for the LMC. This is SMC-sized halos. We didn't have an LMC-sized galaxy in this volume. But I would expect that if you go up an order of magnitude mass to LMC-sized galaxies, these numbers aren't going to dramatically shift. And yet we're at a point where some people are claiming like 7, maybe even more of the DES dwarfs are kinematically associated with the LMC. I would be really surprised if we jumped up an order of magnitude mass and suddenly predict that we expect to find 7 ultrafaint dwarfs around the LMC. So, James, you said yesterday maybe it would solve some of the issues in the Milky Way if you shifted the DES dwarfs to the LMC, but really then I think it just creates an LMC problem, right? So it doesn't actually go away. So yeah, point being, I think we're at a point where we really need to worry about how many dwarfs do we expect around the Milky Way and the LMC, and I don't have a good answer. We're digging into it at this point. So that actually brings me to my conclusions, as I think I'm about to be told that I'm done. So yeah, we're creating this sample of hundreds of dwarf galaxies in order to interpret the local volume. And we have so far looked at things like the scatter and the stellar mass to halo mass relationship, the role of black holes, and we are looking at what density do we actually think the first stars are forming in these galaxies. And because that's going to have implications for what we expect with LSST. Okay, thanks.
Thank you. I apologize for being late. Questions, Joel?
2 quick questions. As you know, the Saga observations are showing that Milky Way analogs often have star-forming satellites.
Right.
Can you say whether your, I guess this is the DC...
The DC Justice League runs, yeah.
And then the second question, when black holes merge, unless they have just the same mass and are aligned, you're going to get a kick of at least a few hundred kilometers per second, which should be enough to remove the black hole, the merged pair, from these dwarf galaxies. Are you taking that into account?
So I'm actually going to lean on Michael for the second one there, but I'm pretty sure kicks aren't in here at this point. I think Jillian was planning on putting black hole kicks into it and exploring the impact. For the satellites in the Milky Way runs, to be honest, I have not actually looked yet at these results, but in the previous set of Milky Ways that we ran, which had basically the same feedback prescription, right, star formation feedback prescription, and were the same resolution, they did have some star-forming things. Now, at the time, I thought maybe that was, they were also the old SPH, where that didn't properly account for the Kelvin-Helmholtz instabilities, and I thought maybe that's what was going on. But now I'm thinking maybe they're just reasonable Milky Way mass galaxies that have star-forming dwarfs. So yeah, we'll look into that further.
Any other question? Well, lots of questions. Yeah, Daniel there.
Right. So I don't have that answer off the top of my head. We're fitting cores to them all right now, but I don't, like for that one, I don't know what the answer is off the top of my head. I could look into it this morning and get back to you.
We'll take one question more while, yes, Red.
Yeah, so no, right? Because in Charlotte's H2 prescription, there is additional cooling from molecules. Right. It is the same in terms of, all your normal elements, right? At high temperatures down to metal cooling, and then there's an additional molecular cooling, I think, down. Yeah.
It's not showing up. Okay, I think we should move on, sorry. Well, I have a last question.
So yesterday, I talked about how I think it looks like we need to start populating like really low mass halos with galaxies. And it's interesting to me that I think you are able to get down much lower if you just adopt this sort of metal cooling prescription that's more like Fire 1. Do you think we can get all the way there? I mean, are you populating like, I was trying to do the conversion in my head, but are you populating most halos with V max greater or smaller than 10 kilometers per second?
Yeah, so in the metal cooling, well, let me actually talk about the H2 run first, because even in the H2 run, we're getting down to, its halos above about 3 times 10 to the 8 in stellar mass are forming, or in halo mass are forming stars.
Like all of them, or?
No.
Okay. It looked like in the
I have that
H2 ones, it
plot
looked like it was
somewhere,
like 10 to the 9 is where things were really starting to go dark, which
Right,
is about
I
20
think
kilometers.
there's a tanking there, right? But so far, like Jeff Weddell did this abundance matching around the Milky Way to see if the number of satellites, like how low in halo mass do you have to go in order to match, and it was down to about 10 to the 8. So even the H2 run is consistent with that result, at least. And the metal cooling run, I don't know if I trust its star formation, right? Those 1 and 2 and 3 star solar mass.
I guess,
particles.
so the point I was emphasizing the central counts, not out to 300. So I really think that it's like the fact that we have 18 ultrafaints within 50 kiloparsecs. And so I think what you're finding is super interesting, because maybe it's telling us something about the physics that you really have to get, to drive it there. So
Yeah, that's what we're exploring. So
Thank you. So let's thank the speaker again.